Imagine you're an engineer walking through an underground tunnel in Egypt. The air is stale, the walls are rough-cut limestone. You're 50 feet below the desert surface, and then you see it. A box, a massive granite box sitting in the darkness. 70 tons, 100,000 pounds. Carved from a single piece of the hardest stone the ancient world knew how to work. You approach it. You run your hand along the surface. It's perfectly smooth, mirror flat. You pull out a precision measuring tool, the kind used in aerospace manufacturing, and check the surface flatness. The reading shows a tolerance of 0.0002 inches. 2 ten-thousandths of an inch. That's the thickness of a human hair divided by 50. You check the interior corners. Perfect 90-degree angles. You examine the lid. It weighs 20 tons and fits so precisely that you can barely see the seam. And here's the thing that makes your engineering degree feel worthless. This object was created 4,500 years ago, supposedly with copper tools and stone hammers. You're standing in front of something that modern CNC precision machines, computer-controlled cutting tools that cost millions of dollars, struggle to replicate. This is the Serapeum of Saqqara, and these boxes shouldn't exist. Welcome to one of the most disturbing engineering mysteries in Egypt, one that most documentaries ignore, one that challenges everything we think we know about ancient capabilities. Because these aren't just boxes, they're precision instruments, manufactured to tolerances that approach modern aerospace standards. And nobody, not archaeologists, not engineers, not materials scientists, can explain how they were made. Let's go underground. Chapter 1. Discovery, the underground labyrinth. The year is 1850. The location is Saqqara, Egypt, about 15 miles south of Cairo, in the shadow of the Step Pyramid. A French archaeologist named Auguste Mariette is excavating in the desert when he discovers something strange, the head of a sphinx protruding from the sand. He starts digging, and he finds more sphinxes, an entire avenue of them, half buried, leading somewhere. He follows the path. It leads to an entrance, a doorway carved into bedrock. Mariette goes inside. What he discovers is a massive underground complex, a labyrinth of tunnels carved into the limestone bedrock beneath the desert. The main corridor stretches nearly 400 feet. Side chambers branch off like the ribs of a spine. The place is called the Serapeum, supposedly a burial site for the Apis bulls, sacred animals worshipped in ancient Memphis. But it's not the bulls that make this place extraordinary. It's the boxes. 24 massive granite sarcophagi, although calling them sarcophagi doesn't do them justice. These aren't crude stone coffins. They're precision-engineered containers that look like they were manufactured, not hand-carved. Each one weighs approximately 70 tons. The lids weigh another 15 to 20 tons. They're cut from single pieces of granite, mostly Aswan red granite and black granite, some of the hardest stone in Egypt. And they're placed in underground chambers barely wider than the boxes themselves. Mariette documented them. He measured them. He tried to understand their purpose. But he never tried to explain how they were made. Because by the standards of 1850s engineering, they were impossible. Fast forward to the late 20th century. An engineer named Christopher Dunn visits the Serapeum. Dunn isn't an archaeologist. He's a precision engineer who spent decades working in aerospace manufacturing, creating parts for jet engines and aircraft components. Work that requires tolerances measured in 10,000ths of an inch. He's seen the best that modern precision manufacturing can produce. And when he examines the Serapeum boxes, he's stunned. Because these boxes, created supposedly with copper chisels and stone pounders, exhibit precision that rivals modern computer-controlled machining. Dunn pulls out precision measuring tools, straight edges, angle finders. He checks the flatness of the surfaces, the squareness of the corners, the parallelism of opposing sides. The results are disturbing. The surfaces are flat within 2 ten-thousandths of an inch across spans of several feet. The interior corners are perfectly square, exactly 90 degrees. Opposing sides are parallel to tolerances that approach what modern mills can achieve. This isn't close enough for ancient handwork. This is precision manufacturing. And it raises a question that nobody in mainstream Egyptology wants to answer. How? How do you achieve aerospace-level precision with copper tools? How do you create perfectly flat surfaces on the hardest stone without modern grinding equipment? How do you cut perfectly square interior corners? Something that's geometrically difficult even with modern routers. The official answer is chisels, pounders, and sand abrasion over many years. But engineers who've tried to replicate this work say that answer is nonsense. Let's look at why. Chapter 2, the material science problem. To understand why these boxes shouldn't exist, you need to understand granite. Granite isn't a single mineral. It's an igneous rock composed of multiple minerals, primarily quartz, feldspar, and mica, that crystallize together as molten rock cooled deep underground. On the Mohs hardness scale, granite rates between 6 and 7. For comparison, copper, the primary metal available to ancient Egyptians, rates 3. This creates an immediate physics problem. You cannot cut a material with a tool that's softer than the material itself. A copper chisel hitting granite doesn't cut the granite, it deforms the copper. Mainstream Egyptology acknowledges this problem and offers a solution. The Egyptians didn't cut granite with copper. They used copper tools with sand as an abrasive. The theory goes like this. You take a copper saw blade or tube, add wet sand, which contains quartz particles harder than granite, and saw back and forth. The sand does the cutting. This works in principle. Archaeologists have successfully demonstrated that you can cut granite with copper and sand. But there's a massive difference between cutting granite and achieving 0.0002-inch precision on a 70-ton box. Let's talk about what precision manufacturing actually requires. Modern precision flat surfaces are created through a process called lapping. You take a surface plate, a perfectly flat reference surface, and rub the workpiece against it with progressively finer abrasive compounds. This process removes high spots through selective abrasion. Over many hours, you can achieve extremely flat surfaces. But this process requires several things the ancient Egyptians supposedly didn't have. 1. A perfectly flat reference surface. To create a flat surface, you need something flat to reference against. Modern manufacturers use granite surface plates that are lapped flat to millionths of an inch. Where did the ancient Egyptians get their reference surface? If you say they used another flat granite block, you're just pushing the question back one step. How did they make that one flat? 2. Consistent abrasive particles. Modern lapping uses precisely graded abrasive powders, aluminum oxide, silicon carbide, diamond paste, with particle sizes controlled to microns. Sand is inconsistent. Particle sizes vary wildly. Some grains are angular, some are rounded. This makes achieving uniform precision nearly impossible. 3. Controlled pressure. Precision lapping requires even pressure across the entire surface. Uneven pressure creates dips and high spots. How do you maintain even pressure on a surface that's 10 feet long when you're working by hand? 4. Measurement capability. You can't create precision without the ability to measure precision. Modern manufacturers use granite surface plates, precision straight edges, and dial indicators to check flatness. What measurement tools did the ancient Egyptians use? We have no evidence of precision measuring instruments, no straight edges, no reference standards. And yet, the boxes exist, with precision that modern engineers confirm is real and measurable. Christopher Dunn, the precision engineer who examined these boxes extensively, puts it bluntly. I have worked in precision manufacturing for over 40 years. I know what it takes to achieve this level of flatness, and I know it's not achievable with the tools Egyptologists claim were used. So if copper and sand didn't create these boxes, What did? That's the question nobody can answer. Chapter 3. The geometry problem. Let's move beyond surface flatness and talk about geometry, specifically the interior corners of these boxes. The Serapeum boxes are hollow. Each one is carved from a single piece of granite with the interior cavity carved out. This interior cavity has corners, places where the bottom meets the sides, where the sides meet each other. In many of the boxes, these corners are perfectly square, exactly 90 degrees, sharp, crisp. Here's why that's a problem. Creating a perfectly square interior corner in hard stone is geometrically difficult. When you're carving an interior corner with any kind of tool, chisel, saw, drill, you're limited by the geometry of the tool itself. Imagine trying to carve a 90-degree interior corner with a chisel. As you approach the corner, the chisel handle starts hitting the walls. You can't get the cutting edge fully into the corner. You're limited by the physical space. The result is that hand-carved interior corners are always slightly rounded. There's always a small radius where the two surfaces meet. Modern manufacturers face this same problem. When you mill an interior corner with a CNC machine, you're limited by the diameter of the cutting tool. A 1/4-inch end mill creates a 1/4-inch radius in the corner. You can't get sharper than the tool. To create truly sharp interior corners, you need specialized techniques. EDM, electrical discharge machining, uses electrical sparks to erode material. Wire EDM uses a thin wire electrode, grinding with specially shaped wheels. None of these techniques were supposedly available to the ancient Egyptians. And yet, many of the Serapeum boxes have interior corners that are sharp to within a few thousandths of an inch. Dunn examined these corners carefully. He found corners where two flat surfaces meet at precisely 90 degrees with minimal radius. From an engineering standpoint, this is a red flag. It suggests a manufacturing capability beyond what hand tools can achieve. But it gets stranger. Chapter 4. The impossible dimensions. Let's talk about the overall dimensions of these boxes and why they create additional engineering problems. The boxes vary in size, but a typical example measures. External length, roughly 13 feet, 4 meters. External width, roughly 7.5 feet, 2.3 meters. External height, roughly 11 feet, 3.4 meters. Wall thickness, roughly 16 to 18 inches. The interior cavity is correspondingly smaller, creating a massive hollow granite box. Here's the engineering problem. When you have two parallel surfaces, say the exterior bottom and the interior bottom, they need to be parallel for the box to have consistent wall thickness. Dunn measured this. Using precision straight edges and measuring tools, he checked whether opposing surfaces were parallel. They are, to within a few thousandths of an inch across spans of 10 feet or more. Think about what this means in practical terms. You're carving a massive granite block. You're removing material from the interior to create the hollow cavity. You need to ensure that as you carve deeper, you maintain consistent wall thickness all around. This requires constant depth measurement, reference points, precision layout, careful material removal. With modern tools, this is achievable. You use depth gauges, you establish reference surfaces, you measure constantly. But with copper tools and sand, you're chiseling away granite in a dark chamber. You can't see through the stone to know how much material remains. You can't measure the exterior while you're working on the interior. How do you ensure the walls are consistent thickness? How do you know when to stop? How do you maintain parallelism? The standard Egyptological answer is skilled craftsmen developed expertise over years. But skill doesn't overcome physics. Skill doesn't give you X-ray vision through 3 feet of granite. Skill doesn't magically create measurement capabilities that didn't exist. The boxes themselves are evidence that someone had capabilities we're not accounting for. And we haven't even talked about the most disturbing aspect, the lids. Chapter 5. the precision lids. Each Serapeum box has a lid. These aren't simple stone slabs placed on top. They're precision-fitted covers that create an almost airtight seal. The lids weigh approximately 15 to 20 tons, 30 to 40,000 pounds, and sit on the upper rim of the box. When properly placed, the fit is so precise that you can barely see the seam between the lid and the box body. Christopher Dunn brought a flashlight and tried to shine light through the gap between lid and body. In several boxes he couldn't. The fit was so tight that light wouldn't pass through. This level of fit requires several things. 1. Perfectly flat mating surfaces. Both the top rim of the box and the bottom surface of the lid must be flat. Any deviation creates gaps. Dunn measured the top rims of several boxes, flat to within thousandths of an inch. 2. Parallel surfaces. The lid must be parallel to the base of the box, or it will rock and not seal properly. Many lids sit perfectly level with no rocking, no gaps. 3. Precise dimensional control. The lid must match the box opening. Too small, it falls in. Too large, it won't sit flush. The lids fit perfectly. This implies dimensional control and measurement capability. But here's what makes this truly bizarre. How do you test the fit during manufacturing? These lids weigh 20 tons. You can't just lift them on and off to check the fit. Modern manufacturers would use precision measurement, calipers, micrometers, coordinate measuring machines to verify dimensions before assembly. What did the ancient Egyptians use? And here's another problem. Several of these boxes are in chambers where there's barely space to walk around them. The tunnels are narrow, the doorways are tight. How did they get a 70-ton granite box into a chamber that barely fits it? How did they then lower a 20-ton lid onto the box with precision fit in a space where there's no room for cranes or lifting equipment? The logistics don't make sense. Unless the boxes were created in place, carved directly from the bedrock where they sit. But that creates different problems. If you're carving the box in place, you can't flip it. You can't access all sides easily. You can't use a reference surface plate for lapping. Every possible explanation creates new impossibilities. Chapter 6. The Transport Mystery. Let's talk about how these boxes got where they are, because this might be the most disturbing aspect of the entire mystery. The granite used for these boxes came from Aswan, approximately 500 miles south of Saqqara. Aswan granite is famous. It's hard, beautiful, and durable. The ancient Egyptians quarried enormous amounts of it. But 500 miles is a long way to move a 70-ton object. Modern heavy transport uses trucks, trains, cranes, hydraulic lifts, and precision equipment. Moving a 70-ton object today requires specialized equipment and careful planning. The ancient Egyptians supposedly moved these boxes using wooden sledges, ropes, ramps, and human labor. Let's be generous and say this is possible for the Nile River portion of the journey. You load the box onto a barge, float it down the Nile, hard but achievable. But then you have to get it from the Nile to Saqqara, several miles inland. And you have to get it underground, into tunnels, into chambers barely larger than the box itself. Here's where it becomes geometrically impossible. The main corridor of the Serapeum is approximately 10 feet wide. The boxes are 7.5 feet wide. That leaves roughly 15 inches of clearance on each side, 30 inches total. Now imagine moving a 70-ton granite box through a corridor with 30 inches of total clearance, on a sledge, with ropes, manually. Every slight deviation from center and the box hits the walls. There's no room for error. But it gets worse. Many boxes sit in side chambers. To get a box into a side chamber, you have to turn it. You have to maneuver a 70-ton object around a 90-degree corner in a confined space. Modern riggers, people who specialize in moving heavy objects, say this is extraordinarily difficult, even with hydraulic jacks, rollers, and precision measurement tools. How is it done with wooden sledges and rope? And here's the really disturbing part. Some boxes show no evidence of damage from transport. The corners are sharp, the edges are crisp, the surfaces are perfect. If you're dragging a 70-ton granite box through narrow tunnels with minimal clearance, you expect chips, dings, scrapes. Granite is hard, but it's also brittle. Impact damage should be visible. In many cases, it's not. It's as if the boxes were created in place, never moved at all. But that conflicts with the geological evidence. These are Aswan granite, not local limestone. They came from 500 miles away. So we're back to an impossibility. Boxes that must have been moved, but show no evidence of the movement. Chapter 7. The tool mark evidence. Let's examine the physical evidence on the boxes themselves, the marks left by whatever tools created them. When you work stone with any tool, you leave marks. Chisels leave impact marks. Saws leave striations. Abrasion leaves scratches. Modern forensic analysis of tool marks can identify not just the type of tool used, but often the specific tool itself. Dunn and other researchers examined the Serapeum boxes for tool marks. What they found is puzzling. Some surfaces show no tool marks at all. They're smooth, featureless, like polished glass. This is consistent with extensive lapping or grinding. But lapping granite to a mirror finish by hand would take thousands of hours per box. Other surfaces show unusual patterns, parallel lines, regular striations, marks that suggest mechanical movement, consistent feed rates, uniform depth. These marks don't look like hand tool work, they look like machine marks. Dunn notes that some of the surface patterns resemble marks left by modern milling machines. Consistent tool paths, regular spacing, uniform depth. But milling machines didn't exist in 2500 BC. There's another curious detail. Some boxes have hieroglyphic inscriptions carved into them. These inscriptions are clearly later additions. The hieroglyphs are crude compared to the precision of the boxes themselves. They're carved into the surface, disrupting the precision finish. This suggests the boxes predated the inscriptions. Someone found these precision boxes and added inscriptions later. It's as if the boxes were repurposed, created for one purpose, used for another. The officially recorded use, burial containers for sacred bulls, seems almost insultingly mundane given the precision of the manufacturing. You don't create aerospace-level precision to bury a bull. That's like using a Formula One race car to deliver pizza. Whatever these boxes were originally designed for, it wasn't animal burial. Chapter 8. Modern replication attempts. If these boxes were created with simple tools, we should be able to replicate them with modern technology quite easily. Several engineers and researchers have attempted to do exactly that. The results are humbling. In the 1990s, a team attempted to create a precision granite surface using historical methods, copper tools and sand abrasion. They worked for weeks. They achieved flatness of roughly 1/100th of an inch across a 2-foot span. That's 50 times worse than the Serapeum boxes. Christopher Dunn consulted with modern precision granite fabricators, companies that create granite surface plates for industrial use. He asked them about achieving 0.0002-inch flatness on large granite pieces. Their response: that's extremely difficult, even with modern equipment. We'd use computer-controlled lapping machines, precision measurement, and it would take days of machine time. And we'd charge tens of thousands of dollars for a piece that size. These are companies with millions of dollars in equipment, decades of expertise, computer-controlled machinery, and precision measuring tools. And they find it difficult to match what the ancient Egyptians supposedly did with copper and sand. There have been various attempts to explain this away. Theory 1, the measurements are wrong. Maybe Dunn and others made errors in measurement. But multiple engineers with precision tools have confirmed the measurements. These aren't eyeball estimates. These are measurements made with calibrated instruments. Theory 2, natural geological processes. Maybe the granite formed naturally with these properties. But that doesn't explain the box's geometric shapes. the hollow interiors, the precisely fitted lids. Geology doesn't create rectangular boxes. Theory 3. The Egyptians had better tools than we think. Maybe they had hardened bronze, or steel, or some lost technique. But we have extensive evidence of Egyptian metallurgy. We have their tools. We have archaeological records. There's no evidence of advanced cutting tools. Theory 4. They spent enormous amounts of time. Maybe it took decades per box, with teams of skilled craftsmen working full-time. But the precision is the problem, not the time. You can't hand-lap your way to 0.0002-inch flatness without modern measurement tools. You can't create perfectly square interior corners without advanced cutting techniques. Time doesn't solve the technical problems. Every conventional explanation fails when you actually try to engineer a solution. Chapter 9. The acoustic properties. There's another strange aspect to these boxes that's often overlooked: their acoustic properties. Several researchers have noticed that the boxes have unusual resonance characteristics. When struck, they ring like bells. The sound sustains for several seconds. This shouldn't be surprising. Granite is a good resonator. Many musical instruments use stone for this reason. But what's interesting is that the boxes seem designed to resonate. The dimensions, the wall thickness, the hollow cavity, all these factors affect resonance frequency. Some researchers have speculated that the boxes weren't containers at all, they were resonators, possibly part of some acoustic technology we don't understand. This is speculative, but it's worth noting that many ancient cultures use sound in ritual contexts. Resonance, harmonics, acoustic properties of spaces. The Great Pyramid itself has been studied for acoustic properties. The King's Chamber resonates at specific frequencies. The whole structure has been theorized as a kind of acoustic instrument. Could the Serapeum boxes be part of something similar? It's impossible to say, but it's curious that such precision would be invested in objects whose official purpose is bury sacred bulls. The precision suggests function. Engineering this precise serves a purpose. We just don't know what it was. Chapter 10. The chronology problem. Let's talk about dating. When were these boxes actually made? The official answer is around 1300 to 700 BC, during the New Kingdom period, specifically the reigns of various pharaohs who left inscriptions. But as we mentioned, those inscriptions appear to be later additions. They're carved onto the boxes, disrupting the precision surfaces. This raises an uncomfortable question. What if the boxes are older than the inscriptions? What if the New Kingdom Egyptians found these boxes, didn't know what they were, or who made them, and repurposed them as bull burial containers? There's precedent for this in Egypt. The ancient Egyptians frequently repurposed older structures. Ramses II was famous for it. He put his cartouche on monuments built by earlier pharaohs. If the Serapeum boxes significantly predate the New Kingdom inscriptions, then they could be from the Old Kingdom, or earlier. Some researchers have speculated they could be pre-dynastic, created before the pharaonic period began. This is controversial because it pushes us into a period when, according to mainstream archaeology, Egypt didn't have the social organization or technology for projects like this. But the boxes themselves are evidence of technology we don't fully understand. If we date them by their precision rather than by inscriptions, they look more like modern industrial products than ancient artifacts. This creates an uncomfortable timeline problem that most Egyptologists prefer not to address. Chapter 11. What engineers actually think. Let's step back from the theories and speculation and focus on what engineers, people who work with precision manufacturing professionally, actually think about these boxes. Christopher Dunn, precision engineer with 40 years of experience. These boxes exhibit precision that I would expect to see in modern aerospace manufacturing. The tolerances are extraordinary. I cannot explain how they were achieved with the technology we're told was available. Engineers from precision granite fabrication companies. Creating surfaces this flat requires computer-controlled lapping and constant measurement. Even with our equipment, this is difficult and expensive. Doing it by hand is not realistic. Materials scientists examining the surfaces. The surface finish suggests advanced grinding or lapping techniques. The regularity of some tool marks suggests mechanical movement, consistent feed rates that handwork can't achieve. Logistics specialists analyzing the transport. Moving 70-ton objects through narrow underground corridors with the clearances we see would be extremely difficult even with modern rigging equipment. Doing it without damage seems nearly impossible. Notice what these professionals don't say. They don't say, obviously the Egyptians were very skilled. They don't say, given enough time and effort, this is achievable. They say, this doesn't match the technology we're told was available. That's a subtle but important distinction. They're not claiming aliens or lost civilizations. They're simply saying, the conventional explanation doesn't work from an engineering standpoint. And in engineering, you're not allowed to ignore problems just because they're inconvenient. If your calculations say a bridge will collapse, you don't build it and hope for the best. If your measurements don't match your tool's capabilities, you don't pretend they do. Engineers live in a world of physical constraints. Materials have properties, forces have magnitudes, precision has requirements. And the Serapeum boxes violate the constraints that Copper Age technology supposedly operated under. Chapter 12. The uncomfortable implications. So where does this leave us? We have 70-ton granite boxes exhibiting precision that approaches modern aerospace standards. We have tool marks that suggest mechanical manufacturing. We have geometric features that are difficult to create even with modern equipment. We have no evidence of the advanced tools needed to create these features. We have transportation logistics that don't make physical sense. We have chronology problems, inscriptions that appear to be later additions to pre-existing precision objects. And we have professional engineers saying, we can't replicate this with the tools we're told were available. This creates several uncomfortable implications. Implication 1. Our understanding of ancient Egyptian technology is incomplete. Maybe the Egyptians had capabilities we haven't discovered evidence for yet. Advanced tools made from materials that didn't preserve. Techniques that left no archaeological record. This is possible, but it requires us to accept that we've missed something major. That decades of Egyptian archaeology somehow overlooked an entire category of advanced technology. Implication 2. The boxes are older than we think. Maybe they predate Pharaonic Egypt. Maybe they're remnants of an earlier, more technically advanced period that was later forgotten. This is the lost civilization hypothesis. It's controversial because there's limited supporting evidence, but the boxes themselves are evidence of something. Implication 3. We're misunderstanding the tools. Maybe Copper Age tools were more capable than we believe. Maybe there were techniques for hardening bronze or using stone tools that we haven't replicated. But experimental archaeology has tested these theories extensively. We can harden bronze, we can use stone tools. The results don't match the precision we see. Implication 4. The precision is exaggerated. Maybe the measurements are wrong. Maybe the precision isn't as extreme as claimed. But multiple independent engineers with calibrated instruments have confirmed the precision. This isn't measurement error. Implication 5. We need to be comfortable saying we don't know. Maybe the honest answer is, these boxes were created using methods we don't currently understand, by people whose capabilities exceeded what we've given them credit for. This is the most intellectually honest position. It acknowledges the evidence without inventing explanations that don't work. But academia doesn't like, we don't know. There's pressure to provide answers, to fit everything into established frameworks. The Serapeum boxes don't fit. Chapter 13. Why this matters. You might wonder, why does this matter? They're just old boxes. Who cares about precision measurements? It matters because these boxes are physical evidence that challenges our understanding of technological development. We teach a narrative about human progress: Stone Age, Bronze Age, Iron Age, Industrial Revolution, Modern Era, a steady upward climb in capability. But what if that narrative is wrong? What if capability isn't linear? What if ancient peoples achieved things we can't fully explain? Then that knowledge was lost. The Serapeum boxes suggest exactly that. They're evidence of precision manufacturing in an era when precision manufacturing supposedly didn't exist. They're evidence of engineering sophistication that doesn't match the tools we believe were available. They're evidence that our timeline of technological progress might be missing chapters. This isn't ancient aliens. This isn't pseudo-archaeology. This is precision engineers looking at physical evidence and saying, this doesn't match what we've been told. And when the evidence doesn't match the explanation, you're supposed to update the explanation, not ignore the evidence. The Serapeum boxes are real. They're measurable. They're there, underground in Egypt, waiting for anyone who wants to examine them. The precision is real. Multiple engineers with calibrated tools have confirmed it. The problems are real. The logistics don't work. The tools don't match. The timeline doesn't fit. What we do with this information matters. We can dismiss it. We can say, the Egyptians were very skilled, and leave it at that. Or we can acknowledge that we're looking at something we don't fully understand. Something that suggests human capability in the ancient world was more sophisticated than our current models account for. Conclusion: standing before the impossible. There's a reason I started this by asking you to imagine being an engineer in that underground tunnel, standing before one of these boxes. Because that's where the theoretical becomes real. That's where the academic debate becomes physical evidence you can touch. When you run your hand over a surface that's flat to within 2/10,000ths of an inch, when you examine corners that are square to fractions of a degree, when you realize this 70-ton object was created with tools that physics says shouldn't be able to create it. That's when you stop caring about fitting evidence into comfortable narratives. That's when you start asking uncomfortable questions. The Serapeum boxes are not the only evidence of advanced ancient capabilities. Egypt is full of similar mysteries: precision cutting, massive stone moving, geometric sophistication. But the Serapeum boxes might be the most dramatic example because the precision is measurable. It's not subjective, it's not interpretation. You can put a precision straight edge on the surface and measure the deviation. You can check the corners with an angle gauge. You can verify the parallelism of opposing sides. The measurements don't lie, and they tell us something we're not ready to hear: that our ancestors, or someone's ancestors, were capable of precision manufacturing that rivals modern capabilities. They did it without computers, without precision measuring tools, without the accumulated knowledge of Industrial Revolution metallurgy and materials science. They did it with something else. Some technique, some knowledge, some capability we've lost. Or maybe we never had it at all. Maybe it was a different development path, a different way of achieving precision that doesn't match our modern methods. We don't know. And that's okay. We don't know is a valid scientific answer. What's not valid is pretending the mystery doesn't exist. Pretending that skilled craftsmen with copper tools is an adequate explanation when engineers who work with precision every day say it's not. The boxes are there, underground, precise, massive, impossible. The next time someone tells you that ancient peoples were primitive, that technological progress is a simple upward curve, that we moderns have achieved things no previous civilization could match, remember the boxes. 70 tons of granite. Precision measured in 10,000ths of an inch. Created 4,500 years ago with tools that shouldn't have been able to create them. Still there, still precise, still impossible. Still waiting for us to figure out how.